Welcome back to my channel. Today, last time, uh, when we finished the last video, I told you that I will explain about number uh, number 119. Right? Last time we were talking about number 119, the importance of uh, why number 19 is important and what is the significance in its significance in physics. Uh, That's what I have promised last time. So, uh, don't think I am repeating the same thing all over. But which is very important. That's why I'm explaining it once again. Uh, this is 10 square, 10 raised to 4, 10 raised to 6, 10 raised to, we took one more 10 square here, making this 10 raised to 8, the electromagnetic field, right? 3 into 10 raised to 8. If you take 3 of these things, you will get 3 into 1, 10 raised to 8 is the electromagnetic radiation or C. Now, uh, when I stumbled upon this Planck's constant, Planck's constant, this I found that H is equal to 119 times mass of proton divided by speed of light. Uh, So here I got my first 119. Second time I uh, was trying to make the gravitational constant G look like the what do you call um, Coulomb's law, right? I mean, look like epsilon naught, right? I was comparing this with this, and I got G equal to 1 by 4 pi into 119 into 10 raised to 7. This is what I got. So this was the second time I got 119. I'm doing a recap here, and Planck's constant, gravitational constant, and last but not the least, acceleration due to due to gravity. G. It was equal to 4 into 119 into 1.67 into 10 raised to 30 or divided by 81 into 10 raised to 32. That is, this is nothing but 4 times mass of sun divided by c raised to 4, where c is the speed of light. This is the third time around I came across 119, and that's why I told you I will explain the importance of 119, what exactly is 119, and why it is so significant in physics. Okay, so uh, yeah, why it is significant, why number 119 is significant, and what has it got to do with uh, the constants in physics, the most used, most popular, very critical constants in physics. All three are major constants in physics. Of course, you all know the importance of Planck's constant. Planck's constant is the one which is which gives me h equal to in my terms I will explain one nineteen by say this is called the Planck's constant that itself is called quantum. So you can see when you say whenever you say quantum mechanics, you are referring to this quantum, right? So it is so important. It is basically the heart of quantum mechanics, and um, yeah. So and this is as I told just now. I told you one H, two is G, three is small. And these three constants in fact rule mechanics. This is Newton's rules the classical physics, right? Mechanics, let's say mechanics. This rules the quantum mechanics. This is, of course, a part of this. So, what is one-ninety? If you look at the periodic table, we have elements from H is 1. On the right side, you have helium 2 atomic weight. They are arranged in atomic, according to atomic weight, right? So now you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So let's say this will be 13, 14, 15, 16, 17, 18. This will be the 18th one, right? So the kind of there are 18 groups. 14, 15, 16, 17, 18. 18th group. So 18 groups, and you have 2, 3, 4, 5, 6, 7. These are the 7 periods, right? These are 18 groups. These are 7 periods. So, what would be the last element here? Here, the last element is 180. So the periodic table lasts from first element of hydrogen to this is called I think organism named after the what do you call Russian scientist I think. So it's named after him. 118 elements we have. So you might have got an inkling of what I'm driving at. What I'm driving at is the periodic table contains 118 elements. Okay, so once 118 is over, what happens to periodic table? So naturally, if it ends at 118, the next element should come here. 119, 120. Right? If this is 118, then the next table will contain 118 into 2. Right? These will elements. Starting it, the next periodic table would start from 119. It should ideally start from 118. So when it reaches this 118 limit, this 119 I am telling you, it will start with 119 and 120. But in reality, what happens is this 119 is more like the proton, 120 is more like neutron, and 121 is more like the hydrogen atom. Hydrogen atom or superhydrogen, you can call. Superhydrogen atom will be 120. So basically, what is happening here, here, let's say these elements will be now 121, 122. Supposing that the present table is ending at 118, these three form the nucleus of these two form the nucleus, and 121 will be the atom of next first of the next table, first element superhydrogen of next periodic table. So that's the importance of 119. Meaning, when we um, got this, let's say, here, when we got hit, we already have here. When we have this thing, 119 here, this means this is like this proton, which this is basically 119 into 1.67 into 10 raised to minus 27 divided by 3 into 10 raised to 8. Meaning, when 119 protons come together, this is the mass of mass of proton. 119 protons come together, they divide into C number of particles. Right? So this C number of particles is nothing but electromagnetic radiation. This electromagnetic radiation, this thing supplies energy to all of this, uh, the whole of this table. This whole table 119 supplies energy to the whole all elements 118 elements of periodic table. So if it is 1, let's say then only as many numbers you have, the atomic number, those many into this electromagnetic radiation will the H will be supplied. This one will have one H, this will have two H, and it goes on like that. 1811718, let's say, into H. So each atom, as per its requirement, accepts one quantum. So this is basically the importance of 190. As far as I know, there will be no element with number 119. It is like the proton of the next table, and that 119, when 119 is raised, it splits into C number of particles. Okay, so this is where the actually even the uh, what we call particle wave duality comes in picture. These are particles. This is this H is wave, energy is wave. So that is the importance of 190. And yeah, we'll go to next step in understanding the importance of 190 again. Right. This is becoming a big pain for me to look this screen glass. Uh, it's really streamless, but can't have. Mm. Yeah. So we have seen that the table, uh, yeah, the periodic table, periodic table extends from 1 to 118, 1 to 118 is the periodic table. Number 119 is the electromagnetic radiation. It turns into electromagnetic radiation by dividing into 3 to 10 to 8 particles. Now, we have basically what we call off-Bohr principle. Off-Bohr principle says, before that, we should know certain things. The quantum numbers, most important of all in quantum mechanics. Quantum numbers, first is principal quantum number, second is azimuthal, azimuthal quantum number, third is magnetic quantum number, fourth one is spin quantum number. Right? This is denoted by E, this is denoted by Z, I think. Yeah, Z. and then this is denoted by the method is L. This is L. Mm, Magnetic is uh, M. Let's say spin is S. So when what is the principal quantum number? Principal quantum number gives you the number of particles. This is one, two, three, four. So where the electron resides, the number of the shell in which the electron resides will gives you the principal quantum number. Azimuthal quantum number gives you a orbital angular momentum. When these are spinning like this around the nucleus, the angular momentum, orbital angular momentum, is given by the H quantum number. And then magnetic quantum number. Magnetic quantum number provides the same thing, orbital angular momentums, momentums projection on specified axis. Right? Orbital angular momentum. This is orbital angular momentum. Its projection on specified axis is given by magnetic quantum number. The spinors. Now coming to spin quantum number. This gives the intrinsic angular uh, momentum, uh, spin angular momentum rather. How the electron is spinning around itself, that's given by spin quantum. So let us say Aufbau principle says one S2, two S2, two P6, three S2, three P6, three D, 10, four S2, four P6, four D, 10, four F, 14, five S2, five P6, five D, 10, six S2, six P6, 6D, D10. Yeah, okay. 7S2, we don't need the others. That's why I'm skipping them. 7P6, 8S2, let's say. So, this S spin can have values of plus half, minus half. So, this is S will have only two. If this is up, this will be down. Coming to P, P can have like this will be subdivided again. So up, down. Like you have, it can house. This can house only two electrons, up and down, up and down. This can house six electrons. These are, by the way, these are called orbitals. D can house up to 10, like 1, 2, 3, 4, 5. and 10. So 10 again, up down like that. F orbital can house up to 14. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So these many electrons they can house, and have the alpha principle of meaning building up in Germany, building up. That building up series, the rule it says, whichever the electrons occupy, whichever orbital has the least energy. Now, by the way, this P can have up to 1, 2, 3, 4 like that, n number of course thing. N can have, what is it, azimuthal, right? Azimuthal, azimuthal can have 0, 1, 2, 3, 4 like that. Whereas this S will take azimuthal value of 0. This is 0. P is 1. D is 2. F is 3. Azimuthal quantum number. Let's say G equal to. Right? So let us see. And then after this, you have magnetic quantum number. For magnetic quantum number, it will contain minus L 0 plus L. It will contain those values. This will of course plus half or minus half to have. This minus L to plus L meaning, let us take an example here, building up. We have, let's say, the, uh, let us say, neon, let us say. Not neon, because we take an example which is immediately precedes the change in structure, right? So that will be 1s2, 2s2, 2b, 1, 2, 4, 4 plus 10, 10 plus 2, 12, 12 plus 6 is 18. Let's say, let us just take the orgon, I think. Orgon could be 18. Or is it argon? Yes, argon is 18. Let us say 1s2, 2s2, 2p6. Till here it is very clear. 3s2, 3p6. How many we have? 10, 18. This is perfect. Till argon, first it fills this one, second it fills this one, third it fills this one, then it fills this one, fourth it will fill this one, then it goes to this one, right? And then what happens is, when we take the example, let's say, let us take one more example. Mm, Now, when we come here, the next mm, after 4s2, so what was that? Argon was till where? To 3p6, till 3p6, or it was argon. After argon, let us take two more and one more, let's say three. After argon, what do we have here? After argon, let us say calcium. Calcium, let us say. Calcium, let us take. Calcium is 20 atomic number. 1s2, 2s2, 2p6, 3s2, 3p6, 18, 4s2, 20. Now, what ideally it should have taken, calcium should have taken here, this value. 4s2, yeah, it should have taken this value following this convention. Till here they were regularly following the convention of cross um, filling of the electrons. But here, when it comes to here, 4s2 and then um, 4s2, 4p6, it should have been like this. But what happens here is, for 4s2, what is the energy? Energy is 4 principal quantum number plus s is 0, it is 4, 3d 10, let us say. If you take the energy of 3d 10, 3, what is the azimuthal quantum number for this is 2, d. So the energy will become 3 plus 2, which is 5, right? So instead of occupying 3d10, it occupies 4s2. Are you getting my point? I mean, any high school student will know this. What I'm saying is the electrons will, according to their energy level given by n plus L, where n is the principal quantum number, and then L is azimuthal quantum number. If you add these two, whichever is least, that will be filled first, and whichever is higher will be filled next. According to the energy, these orbitals will be filled. So, though this is this belongs to the third principal quantum number, meaning, let's say if you have, this is the first one, this is the second one, this is the third one. The electron should have filled this one first, but instead it fills this one first. It doesn't fill 3D. It fills 4s2 before 3. That's the quantum numbers. That's about quantum numbers. Why I am telling about all this is because the whole of physics, encapsulated physics, the physics in a nutshell, can be um, represented by the uh, Aufbau principle. It's like more like the gist of the whole of quantum mechanics, because these were not just like that. These were not found. They didn't find is a quantum number just like that. There was so much research went on, right from Rydberg, Compton. Basically, the main two guys who contributed to this were Schrodinger and then Paul Dirac. Paul Dirac and Schrodinger came up with this uh, the quantum mechanics rather. So they together with, of course, Bohr. Bohr is the one who gave the Aufbau principle. They called it Aufbau principle. So this Aufbau principle is kind of the nutshell, physics in nutshell. So uh, Aufbau principle is physics in nutshell, and we have this value table. It starts with 1, ends with 118. Now our hero comes 119. And as I told you, 119 gives energy to supplies energy to all these elements as per their need. 119 supplies energy. How? In form of quantum. 119 into 1.67 10 h minus 27 by 3 into 10 h to 8. Okay. This 119 number 119 protons come together and they divide into these many particles, and this is a wave, this is a mass, like let's say this is mass, let's say that is mass, this is wave, and through electromagnetic radiation it supplies energy to all 190 elements. That's the importance of 190. So now let us go to a totally different subject. All the while I have been explaining about 10 square, 10 square, 10 raised to 4, 10 raised to 6, 10 raised to 8, all that stuff, right? But I didn't tell you about what if. This is arbitrarily we took it as 2. What if this is 10 cube? This will be 10 cube raised to 2, that is 10 raised to 6. This will be 10 raised to 10 raised to 3 raised to 3, 10 raised to 9. Right? So this basically is a different thing. This is wave, this is particle. In this case, this cube is always, I told you, even here we have 10 raised to 6. That 10 raised to 6, where did it come here? It is a square, right? This was, first one was side, this was square, the whole thing was a cube, right? Or rather, it is circle, this is 4 pi r square, this whole thing was 4 pi r cube, which was, which is a cube. So if you take 10 raised to 6 here, that here from cube to here, this is a square, isn't it? A cube can be expressed as a square here. 10 cube square is 10 raised to 6. So this is where the basic conversion happens. Cube to cube to 3. Let's see. Rather no, square. Cube to square. And then let's forget about that. Cube to square. This was a cube, this became a square here. So we can come up with a different convention for the objects. Like uh, let us say, let us take this 119, 119. I, not this 119. This is uh, what do you call a cone? Cone with radius r. This radius is r from here to here. The radius r, and from here to here. This is the height h, which is also equal to r. Let us say. So what do we get here? A cone whose radius is r, whose height is r. What is the volume of cone? Equal to 1/3 pi r square by r square h. If 1/3 phi or if h is also r, pi r cube. So the volume of cone of radius r and height also r is 1/3 pi r cube, right? And the wonderful geometry doesn't end there. There is more to it in the sense it's a very interesting uh, geometry behind this cone of height and radius, same radius and height. What is the interesting phenomenon here? Volume of cone of radius or and height also or is equal to 1/3 pi r cube. If you take three such 1/3 pi r cubes, what do you get? Pi r cube. And this is one cone, this is another cone, this is another cone of height r, r, this is also r, this is r, of course, this is r. If you take such three uh, cones, what you get is this can also be written as pi r square into r. If this r is h, you can either write it as pi r square h height r, then it will be pi r square h. What is pi r square h? Pi r square h is nothing but volume of radius or and height h. So these are three. There are you can include three cones in one. This is more like that's in fact a cylinder. I'm not making up anything here. You can see for yourself the formula of the pi cube, price for that will give you both pi r square. Pi r square can be expressed as h also, one h separate h, and then if you separate that h, you will get one epsilon. So this has got a lot to do with the volume of cylinder, and all these things have got to do with the fundamental fundamental particles. When we come to fundamental particles, there are called the particles called quarks, leptons, and these are bosons. Right? So uh, let us not go into actually the quarks will be excuse me quarks will be like up quark. Um, mm, let me pull that up. That's better, I think. So this is part of standard model. In standard model, we have these particles. Yeah. Um, yep. That's this is for the Higgs boson, basically, of in the Higgs boson, and these are the bosons. We have up, down, up, down, charm, strange, strange, and a top, bottom. These are the quarks. And for these, you have gluon. For these, you have photon. These are basically force carriers. Bosons are nothing but force carriers for these uh, particles. Yeah. So Z boson here. Yeah, we haven't completed the table. Yeah. This is the electron. Uh, electron neutrino. Neutrino. Then we have muon. Then we have muon neutrino. Muon neutrino. We have tau, particle tau, and tau neutrino. For this is photon. This is a Z boson. This is W boson. And this is, of course, the Higgs particle. And this particle H has energy of 123, around 125 point something uh, giga electron volts. Okay, so now why I deviated a bit here, because ultimately the aim of any um, uh, physicist who is interested in unification is, let us put it in a sentence, the whole progress of physics in one sentence, if you want to put it in, then standard model is the answer. Standard model, more or less, is perfect model which explains which explains including special relativity. It explains everything: the mass of the particles, the spin, the charge, the mass, spin, everything it explains perfectly except for what? What is that? The lack of graviton. Graviton. They included everything except graviton in the standard model. So now let us take this one cone whose radius is r, height is h, h is equal is also equal to r. and we have a cylinder which can be divided into equals of r, height r, and area r. Right? This is one third by r cube. So this is two thirds by r cube, and you can as well have yeah, it is even more interesting is if you take 4 into one third by r cube, what do you get? 4 third by r cube. What is 4 third by r cube? 4 third by r cube is nothing but the sphere. Right? You may think Prasad is explaining things so simply that they're not correct, they can be wrong. No, just because things are simple, they may not be wrong. You know? Most of the people hold that opinion that if something is very simple, it can be, unless you include a whole lot of math rhetoric, a whole lot of equations into that, complicated calculus into throw complicated calculus into that, it won't be a good theory. That's the general opinion of all these. What do you call? What should we call them? Um, blind wild goose chasers. They're chasing wild goose without paying attention to the basic geometry. They are going after theoretical, uh, what do you call, fantastic theories in maths. They are just pure maths. They are not physics. Pure physics will never include any deep math. This math is more important than those equations. You see, you think in terms of spaces, groups, all that heavy stuff. But still, they can't beat this because it's at the basis. So, fourth priority is sphere. This is cone. This is cylinder. And apart from these two, we can also have two more. Two more shapes. This is double uh, dumbbell, dumbbell shape, right? Again, this is R, this is R, height is R, radius is R, and there's one more here I want to draw. This is a sphere plus cone, right? This is the sphere, this is sphere, and a cone above that. Let's say. So what will this be? This was of course I forgot 2 into pi r cube. Like this, what will this be? 5 into pi r cube by 2. These are the basic structures. These basic structures can be associated with what do you call the fundamental part. That's why I do this and yeah, I'm coming to the original subject of finding graviton, which if we succeed in finding graviton, um, we are there. Meaning, the standard model built by so many, starting with Schrodinger, Caldera, Wave, then Younger Lens, then finally um, got Steven Weinberg and Abdussalam. That is about. So we should basically that is the best model so far, theory of unification so far. So if we can find that graviton, elusive graviton, we are there. Right. Now, uh, let us say we have these hadrons. Hadrons are two types, baryons and mesons. If we, these are built up of quarks. And then if the number of quarks is odd quarks, then they'll make baryons. If even number, even quarks come together, they form mesons. Baryons, the best examples of baryons are proton, neutron. Examples of mesons, there are so many, I think, which are not actually, these are not stable, unstable. Let's say now this proton is made of, of two up quarks and one down quark. Neutron, on the other hand, is made up of two down quarks and one up quark. Right? You know that, right? So up, down, proton, proton, this is proton, down, up is neutron. So you can as well, when we thought of this cylinder, that's it. Though these two parts don't look like cones, they are still cones because uh, 3 into 1, 3 into a third of pi r cube will give you pi r cube or pi r square into. This is of radius r, and height r. So this cylinder can be thought of three quarks. So protons and neutrons, the baryons could be of in the shape of this cylinder. So that is one uh, fundamental particle. Next, coming to the next most important particle, apart from baryons and this thing, we have, let's say, if you have a sphere is equal to 4 into, as per our pi r cube by 3. 4 cones, if you take, of height r, then they will give you 4 pi r cube, right? So which is nothing but 3. And keeping this, to keep this in view, remember this, and then we will go to the next part where we will try to come up with the probable shape of gravity. On what basis I am doing that? Why I am saying graviton could look like this? You will know. So I explain. let me rub this off. It takes a while. Okay, now the mass of proton is equal to 1.67 into 10 multiplied, right? This is approximately equal to 5 by 3 into 10 multiplied. So, leave this part because that varies. See, if you go to sun, the mass of sun, let's say, let us right here, mass of sun is equal to 119 into 1.67 into 10 raised to minus 20, uh, 20, decimal 200, yeah, 28, let's say. Or rather, if you take one more, uh, let us think about this, but let us not bother about this part. This is basically 5 by 3. My mass of proton is approximately equal to 5 by 3. And then, if you imagine 5 parts, let's say 5 parts, 5, what do you call pentagon, whatever the shape is, let's say take 5 equilateral triangles or 5 cones. If you take 5 cones, if you take this shape and let's say slice this off, this portion, half it up, in sense each is pi r cube by 3, let's say, there are 5 h pi r cubes, and we take 3 into pi r cube by 3, that gives you pi r cube, which I call it a hadron, and like barrier, like proton. Look, their shape would be like this. I told you, right? So, if we take, on the other hand, you don't hack this off, you don't hack a part of it, retain it. Let's say, if you retain this, you have this two. This represents, let us say, 5. This represents 3. And if you don't cut this off, this whole thing will represent 4. Right? So, 5 by 3, if we take that give you proton or neutron or baryon, let's say, if you take 5 by 5, the whole thing you consider, then what should it ideally give? In my opinion, because this is mass of proton, and what imparts mass to particles? What imparts the mass to particle is Higgs boson. So this is Higgs field. Next, then similarly we can have 5 by 4, 5 by 2, 5 by 1. Rather, no, I'm trying here, I think. Sorry, this should be 5, 5 itself, 5 itself in the sense, this should be 5 by 1 equal to 5, and this should be 5 by 5, which is 1. Right? So we can as well have, instead of just 5 by 1, 5 by, where is the 5 by 3, 5 by 3 was here. Yeah, yeah, it's on here. So this 5 by 3, instead of 5 by 3 and 5 by 5, 5 by 1 only, if you go next step and you take 5 by 4, say, then this should also be a particle. Which particle it is? I propose that this 5 by 4 is, this is the elusive graviton. It is eluding you. This 5 by 4 is the right. In my opinion, I propose that this is the right. This is fixed field. These are proton, neutron, and even baryons. These are the other particles like electrons, electron, and weak Z bosons, and something like that. But definitely, this is correct. So, what is the um, it's, what do you call Higgs boson? Higgs boson 125 something G is energy. Yeah? So, if 5 is equal to 125, let's say, what will be 5 by 4? Not exactly 5 by 4. Let me understand. If this is 5 parts are this, yeah, 4 parts. 5 parts is equal to 5 into 25. This is, if you take 4 into 25 by the same standard, what will you get? You will get 100 bigger electron volts. Last time, while explaining these, what do you call, uh, 10 square, 10 4, 10 6, 10 8, into 10 raised to 8, and C, I took the other one, C, C squared, C cubed, C raised to 4, right? This was 3 into 10 raised to 8, was electromagnetic radiation, quantum world, quantum realm. This was the relative lab, C, right? So I compared these two and said, this 3 into 10 raised to 8 this is the fourth dimension of quantum world, and become first dimension for, of the relative world. And so, yeah, what was that? Quantum realm and this realm. And I said, are we comparing apple of gravity with orange of photon? I told you it is material photon. I call it as a, I will say call it graviton, but it's actually Graviton photo radiation, I call it, DP radiation. So I asked this question, are we comparing two different worlds? But here, this is not a different world. It is, it is very much in the league of Higgs boson, little less than Higgs boson. If X is 5, I propose that graviton is 4. Graviton is 4. So that's my conclusion for the day. It's getting long, so let us call it today for now, and we'll meet some other time when we will try to explore the Schrodinger. Schrodinger is name is as difficult as his equation, Schrodinger equation, as well as Paul Dirac equation, which are the basis of, as I told you, the quantum numbers. What I feel, my gut says that we may need new quantum numbers in the sense one or two new quantum numbers which will give you a different spin, different mass, and different charging, of course. It's not that basically different uh, spin, basically. That you can get only by coming up with new quantum, I feel. So yeah, let us delve deep into that next time. For now, I'll call it today. Thank you very much for watching my video. And we'll meet you week or so. Thank you.